Have you ever counted the petals on a daisy and wondered why there are exactly 13 or 21, never 12 or 20? Or noticed how pine cones seem to spiral in perfectly organized patterns that appear almost too mathematical to be natural? What if I told you that you're not just observing mathematical patterns in nature, you're literally living inside the most important number sequence in the universe, a mathematical formula so fundamental that it governs everything from your own body proportions to the spiral arms of galaxies? Today, I'm going to reveal how the Fibonacci sequence isn't just an abstract mathematical curiosity, it's Emmy Noether's conservation principles made visible, demonstrating how nature optimizes growth, efficiency, and beauty using the same mathematical code that appears everywhere you look. The story begins with numbers that seem almost too simple to be profound. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is simply the sum of the two numbers before it. Leonardo Fibonacci introduced this sequence to Europe in 1202, but he had no idea he was documenting the universe's favorite mathematical pattern. What makes this sequence extraordinary isn't the simple addition rule, it's that these exact numbers appear with supernatural frequency throughout natural worlds, following patterns so consistent they seem like evidence of cosmic mathematical design. Emmy Noether's insights about symmetry and optimization help explain why the Fibonacci sequence dominates natural systems. When plants grow, when shells form, when flowers develop their petals, they're solving complex optimization problems. How to pack the maximum amount of material into the minimum space, how to capture the most sunlight with the least energy expenditure, how to create the strongest structure with the most efficient use of resources. The Fibonacci sequence emerges naturally from these optimization processes because it represents mathematically optimal solutions to fundamental growth and packing problems. Look at your hand right now. You're holding a Fibonacci calculator. 5 fingers, each with 3 segments if you count the palm connection, arranged according to proportions that follow Fibonacci ratios. This isn't coincidence, it's evolutionary mathematics. Your hand evolved to follow Fibonacci proportions because those proportions provide optimal dexterity, strength, and functionality. The golden ratio, approximately 1.618, which emerges from dividing consecutive Fibonacci numbers, appears in the length ratios between your fingers, your arm segments, and even your facial features. The sunflower provides perhaps the most spectacular example of Fibonacci mathematics in action. Count the spiral patterns in a sunflower center, you'll find 2 sets of spirals going in opposite directions. The number of spirals in each direction will almost always be consecutive Fibonacci numbers, 21 and 34, or 34 and 55, or 55 and 89. Larger sunflowers can have 89 and 144 spirals. This pattern emerges because the sunflower is solving a packing optimization problem: how to fit the maximum number of seeds into a circular space. The Fibonacci spiral angle, approximately 137.5 degrees, provides the mathematically optimal solution. Pine cones, pineapples, and nautilus shells all follow the same Fibonacci spiral patterns for similar optimization reasons. The pine cone scales arrange themselves in Fibonacci spirals to maximize protection while minimizing material usage. The pineapple surface hexagons follow Fibonacci counts because this arrangement provides optimal structural strength and efficient growth patterns. The nautilus shell grows in a Fibonacci spiral because this shape maintains constant proportions while maximizing internal volume, a perfect example of how Emmy Noether's conservation principles manifest in biological growth. Flower petals reveal another layer of Fibonacci mathematics that demonstrates optimization principles at work. Lilies have 3 petals, buttercups have 5, delphiniums have 8, marigolds have 13, asters have 21, and daisies typically have 34 or 55. These aren't random numbers, they're Fibonacci numbers that result from genetic programs optimizing petal arrangement for maximum reproductive success. Petals arranged in Fibonacci numbers create optimal symmetry patterns that attract pollinators while using minimal genetic resources to code for petal development. Tree branching patterns follow Fibonacci mathematics because branches must optimize multiple competing demands, maximizing sunlight capture, minimizing weight, ensuring structural stability, and efficiently distributing nutrients. The Fibonacci sequence provides mathematical solutions to these multivariable optimization problems. Count the branches on a tree as they split from the trunk. You'll frequently find Fibonacci numbers governing the branching patterns at different levels of the tree's structure. The human face demonstrates Fibonacci proportions in ways that connect mathematical beauty to evolutionary fitness. The distance from your chin to your eyebrows compared to the distance from your eyebrows to the top of your head approximates the golden ratio. The width of your mouth compared to the width of your nose, the spacing of your eyes, and the proportions of your facial features all tend toward Fibonacci ratios. Faces that closely follow these mathematical proportions are consistently rated as more attractive across different cultures, suggesting that beauty itself follows mathematical optimization principles. But Fibonacci patterns extend far beyond individual organisms to govern ecological and astronomical systems. Spiral galaxies follow Fibonacci spiral patterns because rotating matter naturally organizes itself according to mathematical principles that conserve angular momentum while maximizing gravitational stability. Hurricane and typhoon formations create Fibonacci spirals because atmospheric dynamics follow the same optimization principles that govern biological growth, minimizing energy expenditure while maximizing rotational efficiency. The physics underlying Fibonacci patterns reveal deep connections to Emmy Noether's conservation laws. When natural systems grow or organize themselves, they must conserve energy, momentum, and material resources while maximizing functionality and survival advantages. The Fibonacci sequence emerges from these conservation constraints because it represents mathematically optimal solutions to multidimensional optimization problems. Nature doesn't consciously calculate Fibonacci numbers. The sequence emerges automatically from physical processes that follow conservation principles. DNA structure itself incorporates Fibonacci mathematics in ways that optimize information storage and replication efficiency. The double helix completes one full turn every 34 angstroms, with each turn containing 10 base pairs, numbers that relate to Fibonacci ratios. This proportional relationship isn't coincidental. It represents an optimal balance between structural stability, information density, and replication accuracy that emerged through billions of years of evolutionary optimization. Reproductive patterns in many species follow Fibonacci sequences because these patterns represent optimal solutions to complex ecological optimization problems involving resource allocation, timing, and genetic diversity. The golden ratio derived from Fibonacci sequences appears in architecture and design because human aesthetic preferences evolved to recognize mathematical optimization patterns. Ancient Greek architects used golden ratio proportions in the Parthenon because these proportions create visual harmony that appeals to human pattern recognition systems. Modern designers continue to use Fibonacci proportions because they create pleasing visual relationships that feel correct to human perception. Stock market analysis and economic modeling sometimes incorporate Fibonacci ratios because human behavioral patterns in complex systems can exhibit mathematical regularities similar to natural optimization processes. While financial markets are far more complex than biological systems, the underlying human psychology driving market behavior sometimes creates patterns that echo the same optimization principles that govern natural Fibonacci sequences. Music and sound frequently incorporate Fibonacci ratios because acoustic harmony emerges from mathematical relationships between frequencies. Scales, chord progressions, and rhythmic patterns that follow Fibonacci proportions create pleasing auditory experiences because they resonate with the same mathematical optimization principles that govern natural acoustic systems. The fractal properties of Fibonacci spirals reveal how the same mathematical principles operate across multiple scales simultaneously. A Romanesco broccoli demonstrates perfect Fibonacci spirals within spirals within spirals, showing how optimization principles can be recursively applied to create complex structures with simple mathematical rules. This self-similarity across scales reflects fundamental properties of how conservation laws create organized complexity from simple mathematical relationships. Modern technology applications increasingly utilize Fibonacci principles for optimization problems in computer algorithms, antenna design, and data compression. Engineers have discovered that Fibonacci-based algorithms often provide efficient solutions to complex optimization problems because they mirror the same mathematical principles that nature has been using for millions of years. The connection between Fibonacci patterns and the golden ratio reveal deep aesthetic and philosophical questions about the relationship between mathematics and beauty. The golden ratio appears in classical art, architectural proportions, and design principles across many cultures, suggesting that mathematical optimization and human aesthetic preferences are intimately connected through evolutionary processes that shaped both our environment and our perception. Research into plant growth patterns continues to reveal new applications of Fibonacci mathematics in understanding how organisms optimize resource allocation, structural development, and environmental adaptation. These discoveries have practical applications in agriculture, architecture, and engineering design, showing how understanding natural mathematical principles can inform human technological innovation. The next time you see a flower, count a pine cone, or look at your own hand, remember that you're witnessing Emmy Noether's conservation principles made visible through the Fibonacci sequence. Nature isn't randomly beautiful, it's mathematically optimized according to principles that govern everything from quantum mechanics to cosmic structures. The Fibonacci numbers surrounding you represent solutions to optimization problems that connect the growth of a sunflower to the formation of galaxies, demonstrating that the same mathematical laws operating in the deepest reaches of physics also govern the everyday natural world you inhabit. You're not just observing mathematical patterns, you're living inside mathematics itself, experiencing daily life within the most elegant number sequence the universe has ever discovered. This mathematical ubiquity reveals something profound about the nature of reality. The same optimization principles that Emmy Noether identified in physical conservation laws also govern biological growth, evolutionary development, and aesthetic beauty. The Fibonacci sequence isn't just a curiosity, it's evidence that mathematics forms the fundamental structure underlying both the physical and biological worlds, creating the intricate patterns that make existence both functional and beautiful. If you're amazed by discovering the hidden mathematics organizing your daily experience, subscribe to explore more ways that number sequences, geometric patterns, and mathematical principles secretly structure the world around you. We're uncovering the invisible mathematical architecture that governs everything from the spiral in your morning coffee to the proportions of your face, showing how Emmy Noether's insights about optimization and conservation create the mathematical beauty embedded in ordinary reality. Each video reveals another layer of the numerical patterns that most people never notice, transforming common observations into profound insights about the mathematical nature of existence itself. Hit that subscribe button and join our community discovering the hidden mathematics of everyday life. We're exploring the secret numerical patterns, geometric principles, and mathematical relationships that create the organized complexity you see everywhere, revealing how the same sequences that govern flower petals also structure galaxies. The mathematical mysteries are infinite. Don't miss the chance to see how numbers, ratios, and sequences create the beautiful, functional, and optimized world you live inside every day.